Hello everyone, welcome back to Calculus BC. This lesson 15, we're going to basically find derivatives using trigonometric functions. And in this particular lesson, we're going to talk about the chain rule and we're going to talk about inverse trig. I do want to stress really quickly that the derivatives already written for you guys, not so great. I apologize for my handwriting here. So the derivative of sine is cosine, derivative of cosine is negative sine. Derivative of tangent will be secant squared x. Cotangent is negative cosecant squared x. Secant is secant tangent. And then cosecant is negative cosecant cotangent. A couple things to notice really quickly is that for every c, so every c trig function, you notice that they're negative. So I tell students that c stands for change. So if I ask you to find the derivative of negative cosine, then you would make it positive sine. So whenever you're taking the derivative of a trig function that begins with a c, you're going to change the sign of whatever that is. And everything else is going to stay the same. So the derivative of negative sine will be negative cosine. So just kind of think like that. Notice that all of these things right here multiplying by my prime. So talking about the chain rule for trig functions is that when you find the derivative of, let's say, sine, you find cosine of that same theta, and then you have to multiply by the derivative of the theta. And that's exactly what you see for all of these. One thing that I do really like is that if you know the derivative for tangent, which is secant squared, then the reciprocal of tangent is cotangent, and the reciprocal of secant is cosecant. So they're the exact same thing, just reciprocals of each other. So reciprocal, 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 reciprocal. And again, because it begins with a c, it changes the sign. If you know secant is secant tangent, then the reciprocal of secant is cosecant, which is here, and the reciprocal of tangent is cotangent. And again, because it begins with a c, it's negative. So this is actually pretty awesome that they group up like this. So that's why I put them in different colors, the same colors. We could spend time, which we're not in this video, we could spend time deriving all of these trig functions. I did have right here written out for you guys how we derive the sine derivative, that is secant squared x, by rewriting sine as, tangent, the tangent as secant squared x. And we looked at that as y equals sine over cosine. We used the quotient rule. We used an identity, which is 1, equals cosine squared plus sine squared. And then we did the reciprocal. 1 over cosine squared is secant squared. And that's how we get that. You can derive all 4 of these trig functions based on simple doing quotient rules with rewriting them into sine and cosine. So it's actually pretty cool with that. So we're going to go ahead and focus on just doing some problems on derivatives of trig functions, because these next couple lessons, you guys have done them already. It's just now I'm introducing trig functions to it. So related rates, implicit differentiation, it's all review. It's just now we're incorporating trig derivatives. So the next couple of lessons should actually be pretty straightforward, with a couple of twists and turns I'm going to throw in there at you guys. But most of the part, it's actually pretty basic. So I rewrote this. You're like, what is that right there? So y equals x squared times, I want to write that cosine of 3x. So for us, just our sanity, I'm going to rewrite the question over here nice and neat for us. So I want to do this derivative. So I want to differentiate this. So I hope you guys see that we have to use the product rule. I've got x squared times cosine of 3x. And then I've also got a chain rule I've got to apply for my cosine. So if we're taking the derivative of our function, we're going to do the first, which is going to be x squared. And then just like before, actually this is the first example, so I don't say that before. But as mentioned before, we're going to take the derivative of just the trig function. So we're going to multiply by the derivative of the trig function, which is going to be, again, the c tells me I got to change the sign. And since this is positive, it's going to be negative sine. And then just like before, we're going to leave theta alone. We're not going to do anything with that. And then we're going to multiply by the derivative of theta. So the derivative of cosine of 3x is negative sine 3x times 3. So whatever this is, and it doesn't have to be a simple polygon. It could be another trig function, or it can be some other. We got a lot of examples we're going to do here for this video. You will still take the derivative of the whole thing. And so anyway, so we got first times the derivative of the second, and then we're going to do plus, and then we're going to go ahead and do the second, and then we're going to multiply by the derivative of the first. So it's not that much more challenging, just an extra step. So just knowing that the derivative of cosine of 3x is what you see right here in gray, you're good to go. And the only thing that we can really pull out of this, ladies and gentlemen, to be honest, is really an x, right? There really isn't too much else going on with this problem. Free response questions, I would absolutely leave it that way. I think it's just the easier way of doing it, but yeah. So this is the answer to our problem that you guys see right here. And I just went ahead and flip-flop this because I like to have the negative in the back. Okay, so let's look at question number 2 when I want to differentiate this. So again, we're going to use the quotient rule, but look at what the question's asking us. It says, for what values of x does the graph of f have a horizontal tangent? So we have to remember that when we're looking at the problem, a horizontal tangent has a slope of 0. So this is, where's our rate of change 0? Where's our rate of change 0? What we need to make sure that we do, though, is keep the integrity of our derivative. Really what we're going to do once we have our derivative is we're going to set our numerator equal to 0, right? For horizontal tangents, our numerator is set equal to 0, and for vertical tangents, our denominator is equal to 0. So we still want to keep the integrity of our problem, so when we do the quotient rule, even though we really only care about the numerator, we still want to write out that the denominator should be 1 plus tangent x quantity squared. We won't need that, but we're good for it. So let's go ahead and look at this problem. And so we're going to do our numerator, and then we're going to multiply it by the derivative of our denominator. Well, the derivative of our denominator is going to be secant tangent minus our numerator times the derivative of our denominator. So the derivative of 1 is going to be 0. The derivative of tangent is going to be secant squared. And then all over 1 plus tangent squared, tangent x quantity squared. So if we look at this crazy thing in the top here, right, we're going to go ahead and do secant x tangent x plus secant x tangent squared x minus secant cubed x. Okay, and we're going to set this thing equal to 0. So that's a crazy problem. But we actually have a really awesome thing that's going to happen here. The first thing I want you guys to acknowledge is we're going to go ahead and factor out a secant, right? So everything has a secant in it, so we can go ahead and knock that out. So we're going to go ahead and do a secant x. So what's left here is going to be tangent of x. What's going to be left here is going to be a tangent squared x. And what's going to be left here is a secant squared x. So if you guys look at this problem, you should hopefully see something, especially in this section right here, right? The section right here. So one of the ideas that you guys learned, one of the properties you learned is that tangent squared x plus 1 is equal to secant squared x, right? This is one of the 3 Pythagorean trig identities that you should know. The obvious one is sine squared plus cosine squared equals 1. So you guys can see this. If I manipulate this problem and I move the secant squared over, I'm going to get that secant tangent squared minus secant squared is actually equal to -1. So I can actually now find my derivative as secant x tangent of x minus 1, right? Because this whole thing right here is going to be -1. So this whole crazy numerator actually simplifies down to secant x times tangent x minus 1. So it looks really insane, but it works out to be this beautiful of a problem. And now all we have to do is to find the problem. The answer to the problem is we got to set secant x equal to 0, and then tangent of x minus 1 equal to 0, and we're going to get tangent of x just simply is equal to 1. Okay? So when we look at the problem again, what makes this problem a little bit frustrating is that if you set secant of x equal to 0, you have to look back here at the original. So if secant x is equal to 0, that means that cosine is going to be undefined. So another thing you can think about here is a tangent sine over cosine, and so cosine has to be defined in order for the denominator to be defined. So this one doesn't even exist, so we can get rid of that one. Tangent of x equals 1, well, that's going to be pi over 4, and then anytime it's in quadrant 1 and quadrant 3. So x is going to be 1 in pi over 4, and then any intervals of pi k. So if k is equal to 0, then we're at pi over 4, which is exactly perfect. When k is equal to 1, it's pi over 4 plus pi, which puts us in quadrant number 3. And then again, 2 pi gets us back to quadrant number 1. So any of these work. Again, if you look at restrictions of this, if you had x equals like negative pi over 4, which I know is in quadrant 4, so why that will not work, why it has to be in quadrant number 1 and 3, obviously, tangent has to be positive 1. But if we did pi over 4, then we would get, negative pi over 4, then that would make tangent negative 1, and this would be undefined. So this is our solution. So k can be a negative 1, just put us back in quadrant number 3 on the other side. So that is the solution to this crazy problem. So, that was probably an extreme case of a problem where I'm just teaching you guys derivatives of trig functions, but I like it just because it does a lot of good stuff with, the quotient rule and then identities and then thinking about, does our answer make sense in context to our problem? So we're going to do a couple more examples and then we're going to stop this video. So let's do a problem that makes us less likely to think. So if you guys look at example number 6, this says the limit as h approaches to 0 of tangent of 3 of x plus h minus tangent of 3x over h. You should recognize this. You should recognize this as the definition of the derivative. And it's the formal definition of the derivative that I'm rewriting right here for you. And so what you need to come out of this knowing is that the function that we want to find the derivative of is actually going to be right here. So f of x is actually going to be equal to the tangent of 3x. And remember, this is the formal definition of the derivative. So all I have to do is find the derivative of my function. So the derivative of tangent of 3x is going to be secant squared, again, of 3x. And then I have to multiply by the derivative of theta, which is going to give me 3. So this answer is going to be B. It's going to be B. The last one I want to do on this particular video, the last two actually to make it 5, is questions number 8 and number 9. And then we'll continue on with more examples later in life. So our question number 8 says, find the equation of the tangent line to the graph at the point 0, 1. Well, ladies and gentlemen, this is nothing new. This is actually pretty basic stuff. Just like I said before, you're used to doing the equation of a tangent line. Now I've got a function with a cosine in it. So if you see this, it's going to be y equals the derivative. Well, the y prime is going to be equal to the derivative of x plus cosine of x. So it's going to be 1. And then the derivative of cosine, again, because it begins with a c, is going to be negative sine x. And so we're going to plug in 0. We're going to plug in 0 here. So f prime of 0 is going to give me 1 minus sine of 0. And sine of 0 is just going to be 0, so 1. So my derivative is 1. So I got y minus 1 is equal to 1 times x minus 0. So y minus 1 equals x minus 0. So I get the function y equals x plus 1. X plus 1, which again is b. And that was way too simple, but it is what it is. So the last one we're going to do in this set of notes or this video here is going to be question number 9, where we have an extreme crazy case where we're having to find sine of a theta. And I'm just going to say that. So what I wanted to say about this is that when we're finding this derivative, right now our eye is only focused on sine, and then this is theta. This whole thing is theta, so we don't care about it right this second. So all I care about when I'm taking the derivative of a trig function and theta, whatever it is, and again, this isn't a crazy function, I just want to take the derivative of the trig function. So the derivative of the trig function for sine is going to be cosine, and I'm going to leave theta alone. Just like in the very first example, when we're taking the derivative of cosine of 3x, I would write the derivative of cosine, and then I left 3x alone. And so now we're going to use the chain rule. Now my eye goes to what's inside of here. So you guys can see that now it's cosine of theta. I don't care what theta is. So all I now know is that I care about this trig function. So I'm going to multiply by the derivative of cosine, which is negative sine. And then I'm going to leave theta alone. And then finally, my eye goes to, now this theta, this trig function. And so this one, I'm going to take the derivative of tangent of x. I'm going to get secant squared of x. And if I had to, this is the theta, right? And I would have the derivative of this. So I'm going to also multiply this by 1. So you're working your way outside ed. So we care really about the sine function first, and then we just do the theta, and then our attention turns to the cosine function, and then eventually our eye turns to the tangent function. So again, random examples for derivatives of trig functions. When we do our next video, we're going to do some more examples, but mostly we're going to talk about the chain rule by rewriting our trig functions. So I'll see you guys back in the next video.